early this morning?
Oh, yeah.
How's practice going?
It's good. Yeah, it was nice to be outside yesterday. Oh my goodness. It's like half sunblock and everything. It's crazy.
Be back out there today?
Not today, but tomorrow. Yes.
Good.
I have classes until 5:30 today.
Oh, today's the long day.
That's my long day.
Oh, Kylie? Morning.
I was gonna put it in and I woke up this morning.
Morning, Alex.
Whenever I do it, I do like ready this week. I'm refreshed. So we ready to learn more things. So I'm trying to manifest it. I'm trying to manifest it.
Okay, good morning. So today my goal is to get the rest of chapter 5, and then we'll start chapter 6 on Thursday. So to review, what two things go into torque? What two variables are multiplied together to create torque? Force. Yeah, force and moment arm. So how do we define the moment arm? Distance between 2 points. Yeah, so where the force is applied and the axis. So in the body, our muscles create torque. So the muscles attach on the skeleton a certain distance from the joint axis. And so when muscles create force and they pull on their attachment point, it's the torque that causes joint rotation moment. So torque is the rotary effect of a force. Rotary effect of a force. And so in the body, we have different arrangements. And so we call these leverage arrangements. And there are 3 of those, and some are more advantageous than others. It really depends on the length of the muscle moment arm versus the length of the resistance moment arm. So what is it that creates resistance? What is it that ultimately creates resistance? And if in this class, remember the answer that if you don't know, you just say it. Say the word gravity. Yeah. So our body segments have mass, and then when gravity pulls on the segments of our body, that's what creates weight. And so weight is what our muscles are working against. So in the body, we have 3 different examples. So first, second, and third class levers. So a first class lever, you have 3 parts with each of these levers, but in different arrangements. So you have where the muscle is pulling on its attachment point, and then you have the axis, and then you have the resistance. So think force, axis, resistance. And with each of these different lever classes, those things can be in different orders. So with the first class lever, just what I said with the first example, you have the force from the muscle. So in this case, which Which muscle is that? Yeah, so the tricep has its attachment point on the olecranon process of the elbow here, and so that pulls there on the radius, because the radius is what has the olecranon process, and then the axis is represented by the elbow joint, and then we have resistance here from the forearm and the hand, and then any additional resistance that's being moved by the hand. So with this type of arrangement, how many of you have done, say, cable tricep extensions? So can you see more now? So you can see this in that exercise, how that works. So notice that the moment arm for the muscle is 5 centimeters. So that's how much the muscle has to work with, is 5 centimeters, but the distance between where the resistance is acting and the elbow is 40 centimeters. So the moment arm for the resistance is a lot bigger. So it's 8 times bigger versus the moment arm for the muscle. So what are the implications of that for the muscle?
Must create a lot more force.
Yes, yeah. So if you think about the resistance is creating elbow flexor torque. Because if the resistance is more than what the muscle can handle, what's the elbow going to do? It's gonna flex. But then if the muscle's winning the battle, what's the elbow going to do? It's going to extend. So that's really, in simple terms, what happens with movement is we have muscular torque that competes against resistive torque. So getting back to what we talked about with muscle actions, if the muscular torque is greater than the resistive torque, then it's concentric. So that means we'll be lifting the weight. If the resistive torque is greater than muscular torque, that means the resistance is coming down, and that's eccentric. And then if it's static, where the joint angle is constant, so the torques are equal, then it'd be isometric. So most of the time in the body, the muscles have a disadvantage. So muscles have relatively short moment arms versus resistance. So muscles have to create lots of force to overcome even modest amounts of resistance. So just remember FAR, so force, axis, resistance. So that brings us to a second class lever, where the order of those three things is moved around a little bit. So in this case, the muscle, this is the gastrocnemius muscle that has its attachment point at the calcaneal tuberosity. That's the heel bone. And so we have the force from the muscle. We have the body weight acting down through the ankle joint into the talus. And then we have the axis here, which is just underneath, just superior to the ball of the foot. So force, resistance, axis. Force, resistance, and axis. And so in this case, if you look at the moment arms, you have the moment arm of the muscle, so the distance between where the muscle's producing force and this axis. And then you have the moment arm for the resistance, which is from the axis to, or from where the weight is acting through the ankle joint to the axis here. So moment arm of the muscle is a lot longer than the moment arm of the resistance. So is that a good thing? Does that make it easier to plantar flex? Yeah, so the muscles have an advantage because of the longer moment arm. So how many have done plantar flexion on a leg press machine to work your calf muscles, So generally you can really load up those plates on there to do that exercise. Part of that is just because of this mechanical arrangement. So the muscles have a lot of leverage due to the greater moment arm in this case. So that leaves us with one more. So third class lever, and a good test question would be what's the most common in the body, and that's the third class. So you want to remember that. So third class lever we have going left to right, we have the axis. So that's the elbow. Okay. And we have the force, that's where we have the muscle attachment. And then we have the resistance out here. So axis, force, and then resistance. So this is the most common in the body. Is it an advantage or a relative disadvantage in this arrangement? So you just compare moment arms. You can see that, yeah, so muscles have, again, a short moment arm, and the resistance is, moment arm is a lot longer. So from the hand all the way to the elbow here. So most of the time, this distance is about an inch to an inch and a half, versus however long it is from your elbow to the center of your palm is more than an inch and a half. So that's what the resistance is working with. So when if in this specific example, if the resisted torque is greater, what's the elbow going to do? It's going to extend. If the muscles are winning, what's the elbow going to do? It's going to flex. So it's really a question of torques. So competing torques that rotate joints. So resistance creates torque, and muscles create torque in opposition. So going further into this, anyone recognize what joint this would be? Knee joint, okay. So the quadriceps have their insertion through the patellar tendon on the tibial tuberosity here. So this creates an angle between the patella, which is embedded in the quadriceps tendon, and this attachment point is this angle of 35 degrees. So that angle would change as you go into greater knee extension or greater knee flexion. The purpose of the patella is to lengthen the moment arm of the quadriceps tendon. So because of the patella, the quadriceps tendon is located a little bit more or a little bit further from the axis of the knee joint. So because our moment arm here is lengthened just a little bit, the quadriceps has greater torque. So the force from the quadriceps combined with the length of the moment arm here would give the quadriceps more of an advantage. So lengthening the moment arm through the patella. So what type of bone is the patella? We have a few of them in the body. One just underneath in the ball of the foot for the extensor hallucis muscle. So it's a sesamoid bone. And so that's what sesamoid bones do, is they give muscles a little more advantage by stretching the moment arm. Okay, so let's talk about hip extension. So as I look, all of you have probably done both of these exercises. I taught for 11 years in Illinois, and this is one of my students, Aaron Carter, that after he graduated in Illinois, he moved to Houston. He's a personal trainer now, so he's doing really well. But he let me take a couple of pictures for this example. So the good morning exercise, how many have done that one? Yeah, okay, and then this would be a parallel back extension exercise. So we've done that one too. So they're both hip extension, but they have some subtle differences. In the good morning exercise, at this 90-degree angle at the hip, so roughly a 90-degree angle, the hamstrings are lengthened over both attachment points. So the hamstrings are stretched at their attachment at the hip and also their attachment at the knee joint. So if we think of the hamstrings as kind of like rubber bands, this really stresses and puts a lot of strain on the hamstrings, which isn't, I'm not saying it's a bad thing, but it stretches the hamstrings over both attachment points at the same time. So there's a lot of strain on the hamstrings with this movement, whereas in this position right here, we get the greatest resistive torque. And so in this position, the hamstrings are shortened at their attachment at the hip and lengthened at their attachment at the knee joint. So the point is that even though these are both hip extension exercises, the greatest amount of torque comes at different angles. So with this exercise, the greatest resistive torque is at a 90-degree hip angle. And with this exercise, the greatest resistive torque is at 180 degrees at the hip. So they're both hip extension, but they're different. So the way that the muscle's being worked is different in each case. So one is not necessarily better than another. They're both good, but they have their differences. So let's talk about a good morning exercise. So what is the total hip extension torque during a barbell good morning exercise at a 90-degree hip angle? So if this is where we get the greatest amount of torque at 90 degrees, and everybody's getting their papers out. I love that. Thank you. How can we calculate how much resistive torque we have? So we have to make a couple of assumptions. So the first assumption is that the spine and the pelvis are locked as one segment. So it's the pelvis and the torso that are rotating about a fixed femoral head. So you have spine and pelvis rotating about the fixed femoral head. So the cue is to think a hinge there at the hips. And so the hips flex to 90 degrees, and so you have to, if any of you have tried to do that, you have to really have good hamstring flexibility to keep your pelvis in position. If your hamstrings aren't flexible, your pelvis is going to tilt back, and then your lumbar spine is going to flex, and that's not good. So you have to have good hamstring flexibility to begin with. The knees are slightly bent, so that's constant angle. The individual weighs 200 pounds, so that's significant because not only are we lifting the barbell, but what else are we lifting? Everything above the hip joint, right? Yeah, so torso, pelvis, head, we're lifting all of that in addition to the barbell. So the head, the arms, and the trunk. So the hat, the head, the arms, and the trunk comprise 68% of your weight. So that's how much weight we're lifting is a fraction of 200 pounds. 68% of 200 pounds would be the combined weight of the head, the arms, and the trunk. So the center of mass of the head, arms, and trunk is 16 inches from the hips. So that's where the collective mass of the head, the arms, and the trunk is located. So that would allow us to measure the moment arm from the hips. So the hips is our axis, and then the overall balance point where that mass is concentrated would be 16 inches above the hips. Okay, so a couple more assumptions. So let's say 135 pounds on the shoulders. And the center of mass of the additional load on the shoulders is located 22 inches from the hips. So you've got two torques that are acting about the hips that you have to add together. You've got the head, the arms, and the trunk that create torque due to weight, and then the additional weight that is being held on the shoulders also creates torque. So we can calculate the resistive torque for those parts and then put those together to create the total torque. And so movement is performed slowly to minimize the effects of momentum. So we're just talking about how much torque the hamstrings have to overcome. Okay, so we got some steps. So 200 pounds multiplied by 0.68, so everybody do that. And how would you convert that to newtons? A couple different ways to do it. Well, you'd want to, that is close. What would you have to do to pounds before you? Yeah, so however many pounds 200 by 0.68 is divided by 2.2 to get your mass, and then you got to multiply your mass by 9.81 to get newtons. Let's use positive 9.81 because we're looking at the reactive torque from the hamstring. So let's stay with a positive 9.81. So you should have a certain amount of newtons for the head, arms, and the trunk. So what are you coming up with?
606.
Okay, good. Everybody consistent? Okay. All right, so let's convert 135 pounds to newtons. So that's the weight of the barbell on the shoulders. So 135 divided by 2.2 will give you the mass multiplied by 9.81. Okay, so we have two weights. Don't put them together yet. Don't put them together until we have torque. So we need to convert 16 inches because 16 inches is the center of mass for the head, arms, and trunk collectively. So 16 inches above the hips would be where that mass is most concentrated. So to do that, you'd multiply 16 inches by 0.0254. 0.0254 multiplied by 16 inches will give you the moment arm in meters. So remember, you have to have newtons and meters to have torque. So then step number 5 is the 22 inches. That's where the barbell is located from the hip. So 22 inches multiplied by 0.0254 gives you the moment arm for the barbell in meters. Okay, so now you should have two forces and 2 moment arms. So now you should be able to calculate the torque of the hat. And the torque of the hat. So you have whatever you got up here for newtons multiplied by whatever you got in step 4. So basically step 2 multiplied by step 4 to get the Newton meters. So the resistive torque for the head, arms, and trunk about the hip joint. So then you calculate the torque of the additional load. So whatever you got for step 3 multiplied by step 5, that'll give you the resistive torque for the barbell. And so now you've got 2 torques. And so you just add your result from number 6 and number 7. I'm just going to walk around for a moment and just check in. Making sense? Okay. Where are you guys? Yeah. Good job. How you doing? Okay. Yeah, good. Caitlin, you doing good? Yeah. Yeah, good. Everybody good? Makes sense, actually.
Yeah, I mixed up the stats because I didn't have 5. I combined those.
We can understand what.
Yeah.
Okay. At least, good. Makes sense. How you doing? Good? How you doing? Okay. All good up here? 582. Where did he come up with that? Okay.
What was the units?
Newton meters. So. That's how much resistive torque about the hip. So you'd have to have muscle activation to overcome that in order for the weight to be lifted. You'd have to have more than 582, whatever the decimal was, Newton meters. Are we ready to, everybody comfortable going further? Okay, all right. All right, so let's look at resistive torque in a little bit more practical way with involvement of hip extensors versus knee extensors. So where the bar is positioned can determine the amount of torque produced by muscles that cross a given joint. So as we look at different types of squats with different bar placements, we have different moment arms created at the hip and the knee joint. So remember, gravity is going to be acting vertically, straight down, and so that is represented here by this dashed line. So this is the bar for a front squat. This would be the bar for a high bar back squat. So that one is held on the superior part of the trapezius. For a low bar back squat, it's more across the mid trapezius and posterior deltoids. So you can see the bar, and then I call this the line of action for gravity. Line of action for gravity. So where the bar is held creates different moment arms at the hip and at the knee joint. So you'd have to create hip extensor torque or knee extensor torque. So let's talk about muscles. So maybe you've had kinesiology. Do you remember what the key hip extensors were? Oh, but you. Yes, gluteus maximus and hamstrings are the two major ones. So gluteus maximus and hamstrings collectively create this hip extensor torque. And then, of course, the knee extensors are the quadriceps, are the prime movers there. So the length of the moment arm would tell you which group of muscles receives more emphasis. So with a larger moment arm, so represented by a greater distance between the knee joint and the line of action, would tell you that there would be more quadriceps involvement. So that would require greater torque from the knee extensors. Whereas, what do you notice the pattern here in the moment arm for the hip extensors as we go from here to here to here? Yeah, so which would mean that you'd have more torque required from the hip extensors, so glutes and hamstrings. So moment arm is really important because that determines which muscles are receiving the emphasis. So the practical message would be we have more quadricep involvement with the front squat because of this longer moment arm. As we progressively move the weight to the other side of the body, we have greater involvement of the hip extensors there because of the difference in moment arm. Okay, so that seems pretty simple and straightforward, but things are never that simple when we're talking about the body. So I want to gradually expand our discussion here. Here's an example of where we have the knees unrestricted in a squat versus with the knees restricted. So there's a piece of plywood here that keeps the knees from moving forward. So in each case, the same depth of squat is achieved, but what's the difference between here and here? Yeah, you have a little bit more hip flexion right here, excellent Logan, which creates greater torque on what? You're going to have a lot more torque at the hip and especially more torque on the low back. So the take-home message of this, and this is from a study published a few years ago, take-home message is you want the knees to have unrestricted motion. So I think a few chapters ago we talked about the pros and cons of knees moving forward of the toes. But if you're doing a deep, at least parallel or even beyond that, full range squat, you have to have some forward translation of the knee joints. Otherwise, you're going to get a lot of stress through your low back region. So a natural good squat involves some forward movement of the knees, and that's enabled by good range of motion here at the ankle joint. So one of the biggest limiting factors in being able to do a good parallel squat or even deeper is range of motion at the ankle. So working on ankle mobility can really make a big difference in how well you're able to squat to those extreme angles. You can see the difference in moment arm here from the hip joint. Okay, so let's talk about muscle activation strategy for a squat, because we know that muscle activation creates muscular torque. So muscles activate, they pull at their attachment point, and that's what creates this torque. So we have torque produced over the hip and the knee joint. So we can look at this in a mechanical sense in this way. So the hip extension net joint torque. So we have two things that go into this. The net torque at the hips is dependent on the hip extensor torque minus the hip flexor torque. So in order to have a positive extensor torque at the hips, we have to have more extensor than we do flexor. Does that make sense? In order for the hips to extend, we have to have more extensor torque than we do flexor torque. Because both of these things together is what creates the net joint torque. So ideally, we want a muscle activation strategy that minimizes hip flexor torque and maximizes hip extensor torque. Questions on that part? So the problem that we run into is the rectus femoris. Rectus femoris has two functions. It acts as a hip flexor, but what else does it do with the knee joint? Yeah, it's an extensor. So the rectus femoris is part of the quadriceps. It's the only muscle of the quadriceps that has action at two joints. So in addition to extending the knee joint, the rectus femoris flexes the hip joint. So why is that a problem? If we're trying to create the greatest amount of hip extensor torque, why would having lots of activity in the rectus femoris during a squat be a problem? It contributes to knee extension, which is good, but what else does it do? It contributes to hip flexion. Now, when the rectus femoris is activated, it tries to do both functions at the same time. So the way that the body works is not isolated to a specific joint when a muscle is activated. So when the rectus femoris is activated to contract, it tries to do both things at once. It wants to flex the hip and it wants to extend the knee at the same time. So that's okay at the knee joint, but at the hip joint that creates a problem because if we're activating the rectus femoris, that creates hip flexor torque. And so that's going to lessen the extensor torque at the hip. So actually what happens is our nervous system is great and it tends to shut down the rectus femoris during a squat. And so by shutting down the rectus femoris, we've effectively minimized the hip flexor torque, which allows the gluteus maximus primarily to create hip extensor torque. So we get the most extensor torque at the hip. Okay, is everybody with me so far? All right, so let's go down and talk about the knee joint. So we want knee extension net joint torque. We want that to be the greatest it can possibly be. So we have two things that go into that. We have extensor torque at the knee, and we have flexor torque at the knee. So to get the greatest extensor torque at the knee, we want to maximize that, maximize knee extensor torque, and we want to minimize flexor torque. Okay, so what does the hamstrings do? They act at both joints. What do the hamstrings do at the hip? Why do we do RDLs? Because the hamstrings do what at the hip? They create hip extension, which is fine. However, what do the hamstrings do at the knee joint? They create flexion. Is that a problem for a squat? Yeah, because what do you want to do during a squat? What do you want the knees to do during a squat? You want the knees to extend, right? You don't want the knees to flex. So we have two competing torques. We have the hamstrings, which extend the hip, which is okay, because we want hip extension. But the hamstrings also create flexor torque at the knee joint, which is a problem. So during a squat, what tends to happen is the nervous system reduces activation of the hamstrings. What that does is it reduces the flexor torque at the knee joint and allows the quadriceps to create the most extensor torque at the knee. So think about it. The quadriceps are trying to extend the knee, but if you have overactivation of the hamstrings, that's working against the objective of the quadriceps, isn't it? The quadriceps want to extend the knee, but the hamstrings are creating torque in the opposite direction. So that would be inefficient, and that would cause the quadriceps to have to overwork to get that knee extensor torque. So what happens is during a squat, because the nervous system deactivates the rectus femoris, is that the primary extensors of the knee joint are the vasti muscles. So any EMG study that you see that involves the squat, you get very high activity of the vastus medialis and vastus lateralis, but you get very little activity of the rectus femoris during a squat. Also with the hamstrings, you find very little activity of the hamstrings during a squat. And so what that does is it allows the quadriceps to do their job. So in summary, if we've taken the hamstrings out and the rectus femoris out, what's the primary hip extensor then during the squat? Yeah, gluteus maximus, and then you've got the knee extensors, the vastus medialis, vastus lateralis, that are the primary knee extensors. Okay, so that's the ideal. That's the ideal. So we run into problems. What if you have very weak glutes? Why is that a problem? Because now your body says, okay, the glutes are weak. What are you going to rely on then to extend the hip? Hamstrings, okay? But if you're overactivating hamstrings, then what muscle group has to work a lot harder to extend the knee joint? Makes the quadriceps work a lot harder, which tends to lead to patellofemoral syndrome. Okay, so it tends to lead to knee problems, all because of weak glutes. So very, very important to strengthen the glutes, because you have stronger glutes, then you can turn off the appropriate muscles and you have good squat technique. So this exact phenomenon was examined back in 2015. This study, quadricep effort during the squat exercise depends on hip extensor muscle strategy. So quadriceps effort depends on what's going on at the hips. Isn't that interesting how the body's all connected together? So this is one quote from the study. In barbell squats, hamstring activation must be minimized so that co-contraction at the knee does not require quadriceps to exceed its strength capacity. So if the hamstrings are overactivated, then the quadriceps have to work a lot harder to get the knee joint to extend, because hamstrings are pulling in the opposite direction. Therefore, a hip extensor strategy prioritizing what muscle? Gluteus maximus is required. Both gluteus maximus and quadriceps, okay, referring to the not the rectus femoris, but the vasti muscles, are limiting factors in the ability to squat heavy barbell loads. So gluteus maximus, very important to improve your squat ability. Okay, so this contradicts previous descriptions of hip extensor versus knee extensor dominant strategy. So this is what we started with, the simplistic view. And then we stepped a little bit further into it. A classification scheme that is oversimplified. Okay, so a couple more quotes from the same study. Full squat should be employed to strengthen the quadriceps and improve performance of tasks requiring quadriceps strength, such as vertical jumping. Contrary to common perceptions of the hip extensors, the gluteus maximus and hamstrings may not function synergistically. What does this last part mean? Synergistically, what does that word mean? Yeah, together. So what we're doing is we're uncoupling these hip extensors. So during the squat, we want maximal activation of the glutes, but we want our hamstrings to shut down a little bit because they would make the quadriceps overexert at the knee joint. Okay, so one more. Gluteus maximus weakness may result in hamstring overexertion and subsequent injury. Gluteus maximus weakness may result in hamstring overexertion. Hamstring co-contraction, okay, hamstring co-contraction increases quadricep force because it's working in an opposite direction, and patellofemoral pressure to magnitudes that may cause patellofemoral pain syndrome. So weakness in the glutes can lead to problems with the knee joints. Interesting. So deficient gluteus maximus strength may be implicated in exaggerated hamstring co-contraction. So if your glutes are weak, your body has to use the hamstrings, but that's a problem because the quadriceps are trying to extend the knee. By involving less hamstrings, concomitantly quadricep activation would decrease, reducing patellofemoral pressure. So what I get out of this is with specifically patellofemoral pain syndrome, one of the strategies to address that would be to strengthen what? Strengthen your glutes. How do you do that? Hip thrust, right? Similar exercises to that. Excellent way to strengthen the glutes and reduce pressure on the knees in other exercises like a squat. Okay, so let's go to the upper body now. So we have lots of muscles, lots of forearm muscles, okay, lots of muscles that flex the wrists and fingers that attach here at the medial epicondyle of the humerus. Lots of muscles that you see here that extend the wrists and fingers that attach at the lateral epicondyle. So these muscles and tendons have a lot of stress. So what we're seeing here is this extensor carpi radialis brevis. So that's on the thumb side. The extensor carpi radialis longus, and the extensor carpi ulnaris. So three of the common wrist and finger extensors. So these muscles have lots of different abilities to create torque. So how many of you have ever, my wife rolls her eyes when I try to do this. So I get really pressed for time, and so I grab all the groceries out of the trunk and try to get them in the house at once. Make multiple trips. I need to eat more cornflakes. Okay, so muscle torque with these three muscles, extensor carpi radialis brevis. So you have different angles at the wrist. So this would be a positive angle going into extension. This would be a negative angle going into flexion. So we're looking at the joint angle here in radians. So chapter 6, we'll get into talking about joint angle and radians. So flexion would be more of a negative angle, extension would be more of a positive angle. So you can see the torque angle curve here for these muscles. So the extensor carpi radialis brevis creates most of its torque at, it looks like, somewhere in the middle, kind of a slight positive angle there. Extensor carpi radialis longus is kind of the same, kind of a positive angle, but the extensor carpi ulnaris, it looks like most of its torque would be created with more of the wrist in flexion. So it's kind of interesting how different muscles have different amounts of torque based on the joint angle. Okay, so next problem, talking about pole vaulting. So what is the total clockwise torque? Total clockwise torque. So this is a torque that's going to turn the vaulter onto their back as they begin going up into the air. So you'd want to add up all the torques that are acting on the vaulter's body. So you have one here of 1,500 newtons that's acting 1 meter from the center of mass or center of gravity. That's the rotation point. Then you have another force that's acting 0.5 meter from the center of mass or center of gravity. So pretty simple, pretty straightforward. You just calculate both torques, 500 or 1,500 times 1, 500 times 0.5, and then you add them together. What'd you get? Yeah, 1750 Newton meters. Newton meters are the units we use for torque. Okay, so this one's a little more involved. How many have tried to do this? It's pretty tough. Never tried. Want to. What do you call this? It's called the iron cross. So you have to have really strong, obviously, upper body to do this. So let's take a look here. Okay, so this gymnast, let's say, weighs or has a mass of 60 kilograms. So can you calculate weight from that? So let's use positive 9.81. So you want to calculate their weight to start with. So this is a static position. Okay. So everything in equilibrium. So the weight, what'd you get? 5 something? Yeah, so about 588 newtons is the weight. So we have moment arms here, so that'd be from the shoulder joint to where force is being applied to the rings. And so our moment arm is 0.6 meters. And so the gymnast applies a downward force to the rings. What do the rings do? They apply an upward reactive force. So if his muscles are not activating, what are his arms going to do due to that reactive force? They're going to go up like this. So he has to maintain that downward force because of this reactive force from the rings. The rings are creating shoulder abduction, whereas the force from his muscles is creating an adductor torque. So we have two torques acting. We have in yellow the reactive force from the rings, which creates shoulder abduction. abductor torque with a B, abductor torque, shoulder abductor torque. And then we have the force from his muscles that create shoulder adductor torque. So how many have heard those terms before? Abduction, adduction. So his muscles are creating adductor, shoulder adductor torque. Okay, so let's do some solving here. So a 60 kilogram gymnast holds an iron cross position on the rings. In this position, the gymnast's arms are abducted 90 degrees. Okay, so that's where we have that static position. And his trunk and legs are vertical. The horizontal distance from each ring to the gymnast's closest shoulder is 0.6 meters. The gymnast is in static equilibrium. So what vertical reaction force does each ring exert on each hand? So we're looking for force if the weight is evenly distributed. How would you tell how much force is being experienced by each hand? You just divide his weight by 2, wouldn't you? So go ahead and divide the 588 by 2 to get the vertical reaction force experienced on each hand. Okay, so 294 newtons. So what shoulder abductor torque is exerted by the right ring about the right shoulder joint? So you know how much force on the right hand is 294 newtons. You have a moment arm. Remember the moment arm? It's 0.6. So how do you calculate torque then? 294 times 0.6 will give you the shoulder abductor torque. Okay, so if this person is in equilibrium, meaning they're not moving, what would you assume the magnitude of shoulder adductor torque would have to be? Wouldn't it have to be the same? Just in the opposite direction. So shoulder abductor torque, 294 times point, what'd you get, 176 Newton meters of shoulder abductor torque would have to be countered by 176 Newton meters of adductor torque by his muscles in the opposite direction. So abductor in one direction, we have to counter that with shoulder muscle adductor torque. So they would be equal, 176 Newton meters and 176 Newton meters. Okay. So if the moment arm of the right pectoralis major muscle about the right shoulder joint is 5 centimeters, how much force in newtons must this muscle produce to maintain the iron cross? So remember, we want moment arm in meters, so we're converting 5 centimeters to meters. So who can do that quickly? So in 1 meter, there's 100 centimeters, so it's going to be 0.05 meters. 0.05 meters in 5 centimeters. So I want you to set the resistive torque equal to the muscular torque. Okay, and so you're solving for the muscle force in this case. So you're given the moment arm of the muscle, you're given the resistive torque, which is how much again? Resistive torque is 176 Newton meters. is equal to the muscular torque, which is 0.05 meters multiplied by muscle force. We don't know what the muscle force is. That's what we're solving for. So how do you solve for muscle force then? Yeah, so you need to divide the resistive torque by what? 0.05 meters to get the muscle, solve for the muscle force. You're going to get a lot of force. Why does the muscle have to produce so much force? Very small moment arm. So the resistance is working with a moment arm of 0.6. The muscle's working with a moment arm of 0.05. So the muscle has to produce what, 3,000 plus newtons worth of force to compensate for the smaller moment arm. Any questions on this one? Yes?
So when we were doing the abductor versus the adductor torque, should we imply like is it a vector? So should we put the negative on one side or not?
Let's keep it simple and just call it abductor and adductor in this case. Yeah, good question. Okay, how are we doing on time? 40, okay. Well, let's keep going. Here we go. So center of gravity or center of mass. So these terms, for our purposes, can be used interchangeably. So it's the overall point around which the mass of the body is equally balanced and distributed. So for a person with average proportions, it's going to be about 57% of standing height. About 57% of standing height in the anatomical position. So the center of mass or center of gravity can change positions as we go from the anatomical position to different body positions for movement. So another commonly cited location, it's right in front of the second sacral vertebrae. So anterior to, approximately at the second sacral vertebrae, point S2, anterior to the sacrum. So right here. So the center of gravity does move. It's not always located inside the body. It can be outside the body depending on our position. So it's a point inside or outside the body around which our mass is balanced. So in 1955, Dempster did a study to determine the individual locations of center of mass or center of gravity for different segments of the body. So from his findings, you can see here for the head, the relative mass. So if you add this column up, it's going to equal 100% of mass. So the head, the center of gravity is located almost 60% from the vertex. So that's the top of the head. And the head makes up almost 70% of your mass. And so you can see other parts here. So the forearms, 45.7% from the elbow. So from the elbow, if we're looking at from the elbow to the wrist, this point is going to be closer to the elbow. Why? So it's not 50%, it's only 45%. So why would the center of mass of the forearms for the average person be closer? And well, most people, but some people would actually be even closer to the elbow. Why closer to the elbow? Yeah, that's where the mass of your forearm is. It's closer to the elbow, not closer to the wrist. So shanks, that's a term used way back then for this segment from the knees to the ankle. Knees to the ankle. So you can see that segment, 44.6% from the knee joint. So not halfway, but closer to the knee. And that would take into account where the mass of the calf muscles are located. So this is really great information because if you're doing a scientific study and you really want to know what someone's lifting, they're lifting external weight, but they're also lifting their body weight. So you can use these estimates to figure out how much of someone's total mass they're actually lifting. There was one time I did do this with a squat study, and for everything above the knee joint is what we accounted for the body mass that was lifted. Because with a squat, are you lifting anything from the knee down? No, it's the knee is bending. Most of it is from the knee up that you're lifting. So, okay, so just another sport-specific example with a high jump. As the athlete bends their body over the bar, it's interesting. They can have a successful jump, but the center of gravity might actually be below the bar because of the way the body is proportioned below and on either side of the bar. Okay, so locating the center of gravity, how do we do that? So if we have a body or object positioned in a certain way, how do we locate where the balance point is? The point around which the mass is equally distributed. So we have this equation where we add up all the individual torques, and if a body or object is in equilibrium, we set that equal to the sum of the weights multiplied by the center of gravity location. So we're solving for R subscript CG for center of gravity. Okay, so let's end on this problem for today. So let's work on this, and then we'll call it a day. So how many of you have ever experienced this where you mistakenly put more weight on one side of a barbell versus the other? How many of you have gone to pick up the weight before you realize it? Yeah, so it kind of, you get a little bit imbalanced there. So that's what we're studying here, is how do we define where the center of gravity is if a barbell is loaded asymmetrically. So a couple of things we have to do first. We have to set our axis. We have to define where our axis is. Now, if you were to place the axis on this side, it wouldn't matter. You'd still get the same answer, but for this problem here today, let's just say the axis is on the right side. So this circle, that's your axis. So all of the weights, including this plate, including the weight of the barbell, we're assuming that the center of mass for the barbell is exactly in the middle. So you have a nice barbell, the uniform composition throughout, so it's going to be right in the middle. And then you have this plate, which is this distance. So you see all of these distances from the axis to this plate, from the axis to the middle of the barbell, from the axis to the very end where this plate is located. Everybody with me so far? Okay, so let's read the problem. A weightlifter has mistakenly placed a 20-kilogram plate on the right end of a barbell. So this would be a 20-kilogram plate, and a 15-kilogram plate on the left end of a barbell. So this would be your 15-kilogram plate over here. The barbell, so that's the third weight, is 2.2 meters long. So standard barbell, 2.2 meters, and has a mass of 20 kilograms. That's 45 pounds. Okay, without the plates on it. The 20-kilogram plate is located 40 centimeters from the right end of the barbell. So That's what R1 is 40 centimeters. So you'd want to convert that to meters quickly. How many meters would that be? 0.4 meters. And the 15 kilogram plate is located 40 centimeters from the left end of the barbell. Okay, so let's figure this out. So the 15 kilogram plate is placed right here, 40 centimeters from the left end. So if you know that the barbell is 2.2 meters, and this plate is placed 0.4 meters from the left end, can you solve for what this distance would be from our axis to here? So what's 2.2? That's the total length of the barbell minus 0.4. 2.2 minus 0.4 is equal to what? 1.8 would be this distance. So from the right end of the barbell to where the 15 kilogram plate is 1.8 meters. Because the barbell is 2.2 meters long, the distance from this plate to the end would be 0.4, so 1.8. Where is the center of gravity of the barbell with the weight plates on it, axis and the right end? Okay, so we need to convert kilograms to newtons. So let's do that to start off with. So 20 kilograms multiplied by, let's do positive 9.81. So these, you need to write down these numbers. So 20 kilograms times 9.81 is 196, is there a decimal? 0.2 newtons. So anytime you have 20 kilograms, you're going to remember 196.2 newtons. Okay, so 15 kilograms times 9.81. 140, how much? 147.15 newtons for the 15 kilogram. Now remember, you also have to remember that we have this barbell as well. It's 20 kilograms too, so 196.2 newtons for the barbell as well. Let's see. Oh, not there yet. So I think we have everything we need. So you've converted all of your moment arms. So this point in the middle, if a barbell is 2.2 meters, what would the point in the middle be? 1.1. So we have everything we need. We have our moment arms, 0.4 meters, 1.1 meters, and 1.8 meters. Okay, so I want you to use this equation. So you're going to take the torque of each part, add them up to get the total torque, and you're going to set that equal to the sum of the weights in newtons. So you have 196 plus 196 plus 147.15. That's the sum of the weights, and then you're going to solve for the center of gravity. So you've got 196.2 times 0.4 meters. You've got 147.15 times 1.8 meters. You've got 196.2 multiplied by 1.1 meters. And so you're going to put all those together to get the sum of those individual torques. divide the sum of the torques by the sum of the weight, and you get the center of gravity, which. So just looking at this, is the center of gravity of the barbell going to shift to the right or shift to the left? Yeah, it's going to shift to the right because you have more weight on that side. So the middle is 1.1, so you should be getting an answer that's a little bit this way relative to this axis. Anybody got an answer yet? Very good, Levi. That's right. 1.03, 1.04, somewhere in that neighborhood. Walk around.
That's where you go from
Okay, so this is,
I just knew what those equations. Where do we go from there?
and then you'd add up just the weights.
Okay, so you just take.
And then you divide the sum of the weights into that. And
Yeah.
Thank you.
final answer? No good? Jackie, how you doing?
So what you do? Where? Did you already do the first half of the equation, like the left side? Like W1, W, or, that's all here?
Oh, these are the torques, so these are the torques. So you add up these, and then just the
Have
weights.
you,
Just the weights, so 196 plus 196 plus 147.
W1, R5,
That's on the bottom.
so these are all those.
Try one more time.
If you're gonna teach it on yeah, I was gonna say, because I was sure of them all. Because I had 559.
Just to be consistent with.
So you would add all those, you would add those, and then you would take just the weights and add those up.
You're correct, but I like to.
Yeah, you would take all the weights and then throw it on.
Calculate. I wouldn't, if you got the right answer.
Good, I got one.
Allie, you good? Eloise, good? Good. Okay, so questions. So we have a little bit of chapter 5 to finish on Thursday, and then we'll get into chapter 6. So have a few of you for lab on Thursday. Remember racquetball court for overhead press part 2. Thank you, and if you want to just leave your assignments at the end of the table, I'll collect